So let me start that a little better. This is my extended version of CHUMP. So I've added this corner down here, and what I've added here is an input and output instruction. So the way the input instruction works is this multiplexer takes input from the ALU output and from the input, and it sends it to the accumulator. So the accumulator can be loaded with the ALU, or it can be loaded with the input. It's just two different types of load instructions. The output is even simpler. It just takes output from the accumulator and throws it on these LEDs here through a register that gets clocked by a control code. So with those extra control codes for the multiplexer and the output, I've added a second control EEPROM. And I've also used that to simplify some things like the program counter load and the multiplexer, the original multiplexer that was originally done with the high bit of the opcode. I've also added an AND instruction, and all the AND instruction does is it takes what's in the accumulator, and it takes some value that you're putting on the bus, and it ANDs them together bitwise. So 1010 and 1001 will give you 1000 because that 2 to the 4 bit would be, or 2 to the 3 bit would be the only bit that was on in both of them. So that's your bitwise AND. And I've created a short program here just to show all of that off. So the first thing it does is it takes input, and I'm going to input the number 3. We'll do 3, and I'm also going to input this high bit here. So that's all going to load in, and the reason I've got that high bit in there is because I'm going to check that to check if the input is ready or if it needs to loop and check for input again. So you could use that as a kind of confirmation. If you had more instructions, you could do it properly. This one is kind of shoddy, but that's okay. It's I'm limited by the 16 instruction limit on the program EEPROM, so, or rather on the program counter. So then it's going to store that into RAM. It's going to do an AND instruction with only the high bit so that it stays on if it's on. If it's off, then this will all go off. It'll become 0. It is on, so when we do this if 0 check, we move on. And now we repeat it again. We do if 0, or sorry, we do input. So let's input the number 5 this time. Yeah, 5. With the check bit again. So we're going to input that. We're going to store it. We're going to AND it to check the bit, and we're going to do an if 0. Again, we would loop if this was off, but it's not off, so we continue. So now what we do is we load back in the original value. You load it. That was a read and then a load. And then you read another one, the second value you put in, and you add it. And the reason you get that clean 8 is because you can actually ignore the high bit the way I've set this up, because you're adding 8 twice, which is adding 16. Since this is a 4-bit number, that's the same as adding 0. So you just get your output nice and clean, and then you just push it to the output. Nice and simple. And then you have a go-to to go back to 0. So as well as that, that's my extension to the actual CHUMP. But as well as that, since the end of CHUMP, I've been designing a couple of architectures, and sorry for the writing on these already. This is my second take of this video. So this is the first one that I designed after finishing CHUMP, and it functions a lot like an 8-bit CHUMP, a little bit different, but it is a Harvard architecture, which means that it has a separate place to store data in RAM and instructions in program ROM. And the way that it keeps track of its 4-byte instructions, because it does have 4-byte instructions, each instruction is 4 bytes long instead of 1 byte like in CHUMP, is it has this sub counter, and it'll just count 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3. So the first byte going in will go here. It'll always be the opcode. It'll come into this register, and it'll control the ALU as well as some other control bits. And then the following 2 are both addresses. So we go into here, we come into the RAM, And either those are immediate values or they're addresses to pull from in RAM, and that's decided by one of these bits in the opcode. Remember, the opcode stays here because it's in a register. And then they get put on argument bus 1, argument bus 2, they get passed to the ALU, and then the third one will determine where it goes back into RAM. Or it could come from or to port mapped IO, because I have added port mapped IO here. All in all, this is a pretty clunky design because all of the instructions are 4 bytes long. That's a little bit wasteful because not all instructions need all 4 bytes. You're going to end up with bytes that are just zeros, and especially with this just has 256 addresses in program ROM planned out, so that only gives you 64 instructions once you divide it by 4. So overall, I'm not such a fan of this design, but it was a pretty cool exploration of what I learned from CHUMP when I first designed it. This design, however, I'm a lot more proud of, and let me just check and make sure that that's all in the camera frame. Zoom out a little. There we go. So how this works is it's slightly different. It's a von Neumann or Princeton architecture, which means that the instructions and data are all stored together in RAM, and the CPU doesn't really know how to tell the difference between those. That's something that's partially determined by the architecture and the control codes, and it's partially determined by the program. So it will, I'm going to ignore the boot EEPROM for now. That would just be a short stored program to load a program into RAM before you run it, but we're assuming there's already a program there. Each instruction is going to be pointed to by the program counter. It's going to be loaded onto this main data bus, which I've found it's useful to center a design around one main data bus. And then the data bus on the first cycle always gets sent to the instruction register where it's stored. And all the registers here are planned to be transparent registers, which means that they don't need a rising clock edge to latch data. They just need a high signal to pass that data to their output pins, and then when it goes low, they'll latch it, and they won't let anything through. So that goes to the control EEPROM. That's going to decide what's going to happen, as well as this cycle counter, which will just count up 0, 1, 2, 3, 4, right? And then at the end of the instruction, it'll be reset by one of these control codes, and that's how it knows there's a new opcode coming in. But depending on what the instruction is and what cycle of that instruction you're on, you'll do different things. And that could be, send it to the accumulator, send it to the ALU, right? Load an address in. That would take 2 bytes because this has 16-bit addressing. So that gives you like 60,000 addresses. All in all, I really like this design. This probably has bugs in it, this diagram here, but I am working on simulating it in a program called Logisim, and that's been going pretty well so far. If it goes really well, and I think it has a reasonable scope for a real project, I may even tackle the project at some point of really building this thing. I think that would be a really cool project, but it's nice to have been able to take away so many things that I've learned from CHUMP and apply them to these designs and hopefully projects in the future.